stage is yours.
Okay, thank you, and thank you for this nice invitation. So I will try to first explain you how this talk is organized. First, I'm going to talk about intermittent collective motion, and the second part of the talk will be about information propagation fronts in biological systems. So intermittent motion in biological system is typically observed at, I would say, at all scales. And here we will see in E. coli and sheep that they exhibit intermittent collective motion. I will see that we can use the same mathematical framework to describe these two very different systems. So let me start with Escherichia coli. So here I'm going to show you what happens with a particular strain of E. coli, which is the enteromorrhagic one. It's a very pathogenic strain. And here what you see is how they move near a glass surface. So if this, if bacteria, E. coli, does not perform any surface addition, then what you would observe is that they are due to hydrodynamic interaction, I mean, the bacterium will get trapped close to the surface, moving in circles, and so visiting the same area of the space over and over. So now if you think that something of interest may be sitting on that surface, and the bacterium is trapped in these circular trajectories, that clearly is not a very efficient way to explore the surface. But now typically it's not this what you would observe, what I have shown you now in this movie. Typically what you observe is that E. coli perform addition stop events to the surface. This is what you would see. So that is what allow the bacterium basically to break these circular trajectories and explore the surface in a kind of more efficient way. So because the bacterium is performing these stop events, what we could do is we can look at the evolution of the speed of the bacterium as function of time. And if we do that, what we would observe is that basically you get a kind of flip-flop signal, in the sense that the speed is high, then goes low, up again, and so on, as you can see here in this slide. And now if you perform an histogram of the speed, you will realize that the speed is bimodal. It's distributed in a bimodal way, and you can use the local minimum to define a threshold and decide, for example, that if it's below that threshold, we will say that the bacterium is in a stop phase, and if it's above that, we will say that the bacterium is in a running phase. Why to do that? Because in fact, what we want to do is to understand what is the distribution of the run times. So for how long the bacterium is running, and for how long the bacterium is stopping. Now, if you look at the survival curve associated to these two quantities, what you would observe is that the distribution of run times, which is this one, is rather an exponential, but the distribution of stop times is not an exponential. So now what you can do is, okay, since we are talking about two regimes, if we want, I mean, basically the bacterium moving and not moving, one can have a kind of naive, I don't know, perspective of the problem and say, okay, I'm going to use a Markov chain and assume that there are two states that basically I can use to describe the system. So either the bacterium is in the state S, meaning it's stop, or it's moving, and that's it. But if you use a Markov chain with two states, what is going to happen is that you will get the correct description for the runtime distribution, but you would also get an exponential, I mean, a straight line in a log-lean figure for the stop times. And this is not what we observe here. So how can we do using a Markov chain formalism to describe this kind of behavior? Basically, this behavior, what you observe here is the sum of two exponentials. And there's mathematically, there is a relatively simple way of doing that, is to assume that there's two states associated to the stop regime. This is a bit counterintuitive because we were defining just two states, basically two regimes, either the bacterium running or the bacterium stopping. And now we are talking that we need to include three behavioral states, I would call three states, to describe the system, two of them associated to the stop regime. So this clearly, I mean, one may ask what would be that, which are these two states? And in order to do that, what we will do is to revisit the experiments. And if you look at the experiment, what you would see is that the bacterium is moving and at some point makes a stop, but often, not always, but often this stop is going to involve this kind of motion that I hope that you have seen, that is basically the bacterium get attached to the surface and perform this kind of tethered rotation around this position. So we will define the three states I showed you before in the following way. 0 means absence of motion, is when the bacterium performs stop, but without performing this kind of rotation. 1 means that it's performing this rotation, which means that it's adhering to the surface, and state 2 is that, and you have well-defined states, a proper way of defining each state. You can go to the data and basically compute for how long the bacterium was in state 0, state 1, and state 2. That is what you see here. This is basically the survival curves associated to each of these states, and you can compute as well as what is the probability once you are in state 0 of going to state 1, and if you are in state 0 of going to state 2, and so on, which is what I show you here. If you have all that into account, basically what you can do is you can basically, of this relatively complex behavioral circuit, identify the transition rate associated to all the possible transitions. And in fact, we observe that there is two transitions that we can neglect, that are these two arrows from 2 to 1 and 1 to 0. And basically with what we end up having is this kind of circuit. And now what you can do is use all what we learn about this transition between states, where we use the speed of the bacterium to decide what was happening with the bacterium, so in which state it was, in order to define basically spatial model in which we will try to describe the bacterium as an active chiral particle experiencing behavioral shift, which is that means that the speed of the bacterium will be given by a behavioral state, meaning the speed will be different if it's in state 0 or 1. In fact, when it was in state 0 or 1, we saw that there is no net displacement of the bacterium. And so this looks kind of complicated, but the good news is that one can describe what happens with this system in terms of probabilities. This is the probability of finding the bacterium in state I, behavioral state I, in position X with orientation theta at time t, moving in direction theta at time t. So if you have all that into account, what you can do is you can basically write down equations for these probabilities. This gets this long expression, but I mean, basically you can derive that. And the only thing that one needs to remember is that once you have all that, you can derive the effective diffusion coefficient of these guys, which is going to depend on the parameters of the Markov chain, basically on these transitions that we were defining before in this previous slide. So now if you take into account all that, what you can do is basically plot the diffusion coefficient at function of this transition rates. This is the transition 2 to 0, basically from running to the 0 state, no motion. And then what you can see is that there are two limiting cases that are easy to understand. One is the situation where the bacterium performs no stop. then the bacterium is performing this circular motion. In this case, the diffusion coefficient will be not too large, but will not be 0. On the other hand, if this K20 becomes very, very large, then what happens if you stay very little time in state 2, basically moving, which means that the diffusion coefficient will go to 0 because you are basically not moving. But in between, as you can see here, there is a maximum value that maximizes the diffusion coefficient. And what is interesting is that in experiments, basically what we measure is that that bacteria move at the value of K20 that maximizes the diffusion coefficient. And that may look like a kind of a coincidence, but then we look in the literature and in other bacterium and other surfaces, and we found that basically the same kind of result. It seems that bacteria adjust the K20 transition, so the stop events frequency in such a way to maximize the diffusion coefficient, which makes sense if what they try to do is to basically explore in an efficient way the surfaces. Okay, so the take-home message of what I show you is that bacteria explore surfaces by performing transient addition events, and that there exists an optimal stop frequency that maximizes the diffusion coefficient. And okay, there is another point, more speculative, which I'm going to basically skip here. So now I move to sheep. And this is basically, hope that you will see this in the movie, that sheep also perform this kind of intermittent motion. They move and stop. Hope that this is convincing from the movie, and hope that you manage to see this movie. So now what we can do is something similar to what we did with the E. coli. Basically, we can look at the speed of the sheep as function of time. And now what we can do is define a threshold, also looking at the histogram of the speed and defining a threshold. And then you can convert the signal into a binary signal, and in order to define when the sheep is moving and when it's not moving. And now what we can do is basically, we can look at the time the sheep is moving and it's not moving, and look at the statistics of these times. And if you do that, basically what you will learn is the runtime distribution. This is a survival curve. It's also an exponential, but the distribution of stop times is not an exponential. And one needs here to use, again, as at least more than one behavioral state to describe this. And we will end up concluding that we need, again, at least 3 states. And these 3 states here will be associated, the 2 associated with the stop motion with a sheep with the head down, and the other one would be with sheep with the head up. One would be associated with the grazing behavior, and the other basically with the warning or a kind of sheep in alert. Anyway, so with that in mind, what you can do is to measure, as we did with E. coli, all transition rates. And once you have all transition rates, basically you get the circuit. And once you have the circuit, there is something else that one has to include here for sheep. That is the fact that these guys the behavior is highly synchronized. Basically, whenever one of them change to a different state, all the others will follow, will also change state. And the key idea is to use rates that depend on the behavioral state of your neighbor. So you have to see what happens around you, and your transition rate will be modulated by the behavioral state of all your neighbors. Okay, so once you have that into account, you can also go to a model for the displacement of sheep, pretty much in the same way as what I show you for E. coli. And basically what you obtain is something that is quite comparable to what I showed. I mean, something that is consistent with the experimental data. So you get a reasonable description of the data. All right, so with that what I want to basically summarize of this part at least is that what I show you, the procedure I follow for in E. coli and sheep was basically the same. We started from converting the experimental signal associated to the speed into a binary signal. Then what we did is we studied the time the signal, the binary signal was in 0 and was in 1. And then what we did is from this distribution of times, we obtained the number of behavioral states and we obtained all the transition rates. And from that, what we did, we analyzed basically the resulting model. And we found, what I show you is that for bacteria and sheep, we need to, in order to get this intermittent motion, we need to use 3 behavioral states. Okay, now I go to the last part. I think I have very few minutes to basically tell you. Now, this is an experiment with sheep. And if you look at the experiment with sheep, hope that you see this. Basically, this is a larger group. It's not 4 sheep, but rather 100. And then what you see here is that there is, in the experiments, there are waves. And in order to observe waves, transition rates should depend on the distance between neighbors. I mean, has to have a dependency on the position of your neighbors. That would be the proper thing to say. And now what we want to understand is what are the consequences of this type of transition rate that depends on the distance of your neighbors in an active system where the activation implies that the guys will move. Basically, here what we have is red. In what I am going to show you next is red means particles that are static, green means that the particle move, and then we will have a transition from red to green if the particle that is red has some neighbor that is green, and the transition rate that we will use is of this form. Basically, you sum over everybody and weight your neighbors with an exponential function. If you do that, basically what you will learn, or you will quickly realize, is that you can do 2 things. One is, here is, I'm illustrating this in a 1D scenario. Here what you get is this green guy is the guy that is moving, and it will be moving to the left. So if I'm moving to the left, you will see something of this sort. So everybody will start moving this way. And now what you have to realize is that you have flow of particles in one direction while information propagates in the opposite direction. And now what you can think is a different situation. Basically, you start with the guy here in green, but moving to the right. In this case, what you would get is that the system will behave this way, as I show you here, which means that the flow of particles and information propagate in the same direction. And basically, what we are learning here is that basically we have this is the 2 examples I showed you before. Now you can start not from the border, but with the particle that is in the middle of a system with everybody everybody is red. And then what you would see is that then the information propagation speed depends on the magnitude and direction of the velocity of individuals. And you can also measure that by performing simulation, for instance, that for small magnitude of the speed of the individuals, there is a linear dependency of the information propagation speed. Now, how can this be understood analytically in a relatively simple way? If you go to a kind of Fisher equation, basically, in fact, you write down the corresponding master equation for the system I showed you before, which is this, is an integral partial differential equation. But then you can make some approximation in this limit with delta A and delta I are very small. And basically, if you do that, you see that this system can be mapped in this limit I'm showing you here in a kind of Fisher equation. And you can show that the propagation speed, c, is a function of the velocity of the individuals. And that explains basically what I showed you before. Basically, the information propagation speed depends on the magnitude and direction of the velocity of the individuals. With that in mind, what you can do is basically now is going beyond the Fisher approximation and taking into account fluctuations. If you do that, there are two things that you can learn. First is that in 2D, in fact, there is no propagation in the thermodynamic limit as you go to negative speeds. And basically you will have a linear relation for positive velocity. I should not put speed here, but velocity of the individuals. And in 2D, what happens is that you can go into negative values, that's possible. And there is a genuine phase transition here at negative values. So, and this transition that you see in 2D, one can show, in fact, that is associated with the critical behavior of the system. So at this point, around the critical point, the system is critical, and that can be shown if one realizes that this system, one can do a mapping from this model I show you with two state to an epidemic SIR model, or if you want in physical terms, in basically dynamic percolation universality class. And this is the weird thing, or which is not very intuitive, is that this kind of system requires 3 states while we started from 2 states. But this can show that effectively the system behaves as having 3 states. I don't know, how much time do I have? I mean, should I finish?
Yeah, I guess your time is over. Yeah, it's pretty much 20 minutes now. You can wrap up, and then we have a few minutes for questions.
All right. So the only thing I'm going to basically mention is the only 2 things that are relevant or I find interesting is beyond the fact that in 2 dimensions the system is has this critical behavior. Then what you can also do is to show that there is the possibility of moving at a speed that is larger than the reaction time of the individuals, which brings to this kind of behavior. Basically, this is, I mean, this is what I want to show you. Basically, this is a regime that we call it the supersonic ship, where the system evolves in this way, which is kind of counterintuitive, I guess. And that's it. I mean, basically, that is all related to the information propagation fronts. So with that, I want to thank the people that helped me with the works I show you. So in related to bacteria, is Stefanote, Emiliano Perez-Ipiña, and from the ship part is Luis Gomez Nava, Sylvain Toulet, and Adrian Gasquel. And the biologists involved is Dorota Shuruka from Monaco and Richard Bon from Toulouse. Okay, so that's it.